So I just realized that 2016 marks the 100th anniversary of the Ramanujan tau function, because the paper written by Ramanujan where he introduces this thing was in 1916. And in that paper, Ramanujan introduced this function. So you have this product n going from 1 to infinity. I've already written this down several times, so I'll write it down again. You write it as a power series in Q. And the coefficients will be denoted tau n. And in his famous 1916 paper, Ramanujan made the following conjectures. I mean, he himself, I believe, calculated a whole bunch of values of the tau function. You can do that very easily just by expanding this thing using the binomial theorem. You know how to expand 1 minus q to the n to the power 24. And you just multiply it out and calculate that. And when you do that, you get a bunch of numbers, and these numbers are all integers. And it motivated him to make the following conjecture. Tau of m times n is tau of m times tau of n for all m and n integers relatively prime. The second conjecture is that if p is a prime number, and alpha is at least 1, then tau of p to the alpha plus 1 equals tau of p tau of p to the alpha minus p to the 11 tau of p to the alpha minus 1. So it's a recursion relation for tau of the sequence tau of p to the alpha plus 1 in terms of the lower ones. And then the third conjecture is the famous Ramanujan hypothesis conjecture, that tau of p, when p is a prime, is always bounded by 2 times p to the 11 over 2. So these are the famous Ramanujan conjectures made in 1916. And it's interesting to note, as a point of historical interest, that conjectures 1 and 2 were immediately proved by Mordell in a very short paper in 1917. But number 3 he didn't know how to do, and he left it. And if you look at the paper by Mordell, it seems to me that the English point of view at the time was that this function and this whole theory of modular forms was more of a curiosity than central theory in mathematics. And so I don't think the tau function received very much attention at that time. And partly perhaps due to cultural perspectives of various sorts. Now, in the same paper, Ramanujan was trying to impress upon the reader why the tau function was important. So he gets a formula. He shows that in the same paper, in his paper, Ramanujan shows that if r sub 24 of n is the number of ways of writing n as a sum of 24 squares, then r sub 24 of n he gets this formula. R sub 24 of n is 16 over 691. Note that 691 again. Sigma 11 of star of n plus E sub 24 of n, where sigma sub v star of n is equal to sigma sub v of n if n is odd. Remember, I introduced the sigma v of n in the previous lecture. It's the sum of the vth powers of the divisors of n, and it's equal to sigma sub v e of n minus sigma sub v o of n if n is even. And here we this is the sum of the vth powers of the even divisors, and this is the sum of the vth powers of the odd divisors. So that's the definition of sigma 11 star of n. What is E sub 24 of n? E sub 24 of n turns out to be equal to 128 over 691 minus 1 to the n minus 1, 259 tau of n minus 512 tau of n over 2. So he knew that the tau function is going to be important if you're trying to understand the number of ways of writing a number as a sum of 24 squares. You will see the resemblance of this particular formula to the Jacobi formula that we got for the number of ways of writing n as a sum of 4 squares. There, the formula was rather simple. You had some of the divisors of n minus some of the divisors which were multiples of 4 or something, very simple. So you had a very precise, exact formula. And you can do this for 6 squares, 8 squares, 10 squares, 12 squares, and so on and so forth. You can do this. And the trouble becomes evident when you start thinking in terms of 24 squares. So for all those other problems up to 24, you can get Jacobi-style formulas in terms of divisor functions. It's only when you hit 24, all of a sudden, something messy happens. You don't get a neat formula in terms of something like this, but you have to introduce this extra term involving the tau function. So this is basically how Ramanujan was thinking about this stuff. I think he had a pretty good sense of what was very important. Clearly, in that fundamental paper of 1916, he was touching upon the foundational ideas of the theory of modular forms. And sad, but the only person who took the cue from this particular paper was Hecke, 1936, which is 20 years afterwards, after the fact, where he understands that there's a big, larger theory going on. So if you try to read Mordel's paper, where he proves his conjectures, they're not very illuminating because it looks very ad hoc and it specializes to the case weight 12. It makes it much more clearer if we try to understand what the general pattern is, what general program is. Okay? So today I want to prove these two conjectures in a slightly general way, and you'll see that the proof is not terribly difficult, provided you have the right concepts. Of course, I'm talking about all this stuff a century afterwards, so it's not fair to say things like that. But anyway, it's not difficult to understand these two. For the third one, of course, as most of you know, or maybe all of you know, you need algebraic geometry to prove this thing, and it is out of bounds of this particular course. However, I'll give you a slightly weaker bound of p to the 6. That's 5.5, right? So I'll get you p to the 6 by the end of the day. Okay, so in order to make progress toward the this conjecture, by the way, Ramanujan made some more conjectures in his paper. I'll come to those when the time is appropriate. And it's actually an interesting paper. I would recommend all of you to rush to the library afterwards and don't fight. Take this book and check out Ramanujan's 1916 paper and see that you can understand quite a chunk of it. Okay, we're going to introduce the Eisenstein series of weight 2. You will remember from last week we introduced the Eisenstein series of weight k, where k was bigger than or equal to 4. And so weight 2, things don't converge so neatly, and so we have to worry a little bit about convergence. And the method of studying Eisenstein series that I'm going to follow is due to Hurwitz. So we'll define the double series G2 of Z this double series we'll define. At the moment, we won't worry about convergence as such. This dash, the dash means that Mn is not, so dash means Mn is not simultaneously 0. Okay. And in order to discuss convergence, we will define A sub m comma n of z to be 1 over mz plus n minus 1 minus 1 over mz plus n. And this for m and n not equal to 0, 0 or 0, 1. Because in the case of 0, 0 or 0, 1, the denominator is going to be 0, and we don't want to have that problem. So we'll define the sequence for those pairs of Mn. Then observe that if I take 1 over mz plus n squared and subtract a sub m n of z, then simple calculation shows that I've got mz plus n squared mz plus n minus 1. So that, and the double series summation 1 over mz plus n squared mz plus n minus 1 converges. Converges absolutely, and there's no problem about it defining an analytic function in that for that thing by the Weierstrass M test. So that's not problematic. Therefore, we can write our series. So I'm going to use this little device trick of subtracting AMNZ and adding it back. Thus, we have G2 of Z equal to, okay, take the term. First, let's take the term m equals 0. If m equals 0, I get n equals minus infinity to infinity, which are non-zero, and I pick up 2 times the value of the zeta function. And when m is not 0, we have and we will write this as 2 zeta 2 plus summation m not 0 subtract am and z. This is only for that tuple m. You see, m is not 0, right? If m is, so we don't have to worry about these two tuples because m is not 0 now, okay? M is not 0, so you would do this, and then we add it back in. All right. The advantage of this thing here is that if I were to sum over all the integers n, so observe, summation n going from minus infinity to infinity of a sub m n of z is 0 because it telescopes. So you see you have this and the opposite signs and then it telescopes to 0 because the series telescopes. And so nothing is lost by doing this little trick, and then we have now convergence because this difference is now of a series which converges absolutely. All right. Now notice G2 of z plus 1 that's because, remember my formula, if you have this formula here, if I replace z by z plus 1, you can see that I'm going to have mz plus m plus n, and that's just a shift on the integers again, so this is clear. And what we would like to see is what happens when, what is G2 of minus 1 over z. I'd like to calculate that and see what that is. And then why do I want to calculate that? Because I would like to know what G2 is doing under the transformations of SL2Z. So remember that SL2Z is generated by the first 1101 and 0 minus 110. So I'd like to check what's going on here. And so what is that? Well, let's put in the thing. So this equals so if I put in that thing, it turns out to be z squared over nz minus m squared. Which equals which equals 2 zeta 2. Now here, I will look at the situation when n is 0. When n is 0, you're going to pick up z squared over m squared. So take that into account and write okay, and then I will take out the Now this is counterintuitive, but I'll take that one of those zeta 2's and put it back in there again. So take the case when n is, I want to throw in n is 0 back in. So when n is 0, I'll pick that back. So m is going to be that. And so I want to put n is 0, m is not 0. And if I were to relabeling m and n, we see that g2 of minus 1 over z equals 2 zeta 2 z squared plus n going from minus infinity to infinity. I just relabeled it, which I recognize now. I'll use this device one more time. So let's take the z squared outside. Put it out there. And I recognize the situation with respect to this thing. And so I see that this can be rewritten g2 minus 1 over z is equal to z squared g2 of z plus z squared times summation n going from minus infinity to infinity, m not 0, a sub m, n of z. So what I'm doing is I'm recognizing this expression here, and I'm looking at it with respect to this, and I see that I can use the same device, the same convergence trick device, by writing 1 over mz plus n squared minus amn plus amn again, and then that's how I pick up this in this order this time. See, this is now a summation over m not 0. Here it was a summation over all the m's. M was fixed. Okay, so you get this. If you shove it back in now, here, I will, because by this device we've managed to interchange summation by this transformation of these indices. So the inside, when I do the AMN trick again, I'm not going to get a telescoping thing. I'm actually going to get this. Okay. When I subtract the AMN, because the thing converges absolutely, I'm able to use this formula and shove it back in. That's how I get the second term. Okay, so you may want to do this a little carefully for the tutorial in the afternoon. Okay. Now, what is the last sum? Okay. Well, let's see what it is. What do we have to do? We have to evaluate n going from minus infinity to infinity, m not 0, of 1 over mz plus n minus 1 minus 1 over mz plus n. Now, this looks awfully familiar. I mean, we were using the cotangent function last week when we were discussing, right? So this looks awfully familiar. So maybe we can rewrite it in terms of the cotangent function. So recall Right? Recall that we met last week, right? Okay. So we can try to, we recognize, okay, so this is a sum over m naught 0, so I might want to make it look like that, n being fixed. So rewriting this as okay, so we do have to worry a little bit about, see, remember in this definition, we have to make sure that n is not 0 or minus 1. So we want to make sure n is not 0 or minus 1. No, that's okay. This is fine. So the inside, what we have is n going from minus infinity to infinity of yeah, I do need to worry about n equals 1 and n equals 0. So we'll remove them. We'll remove those and we'll throw them back in again. But there are two terms when n equals 0 and n equals 1, which I have to worry about. So these are the two terms when n equals 0 and n equals 1 that I have to worry about, and I'm dealing with them here. I put them here because I don't evaluate them. Okay. The summation over m over all, so in order to make it look like that, you can see I have to divide out by z. Oh, there's a 1 over z missing. Sorry. Is that perhaps what you were puzzled up? Okay. There's 1 over z missing there. Okay, so you get that 1 over z times that calculation. Okay, now, this is not a terrible theory, but it's just a little kind of running around with these sums, which once you get the idea, it's pretty straightforward. So maybe I'll kind of skip too many long-winded details. So the last two sums combine to give summation m naught 0 that's because this 1 over mz here and the 1 over mz here cancel. And if I factor out 1 over z, I end up getting m naught 0. Which we recognize as, again, the cotangent business. So the final answer is that it turns out to be minus 2 over z pi cotangent pi over z minus z, which turns out to be minus 2 pi over z cotangent pi over z plus 2. So the last expression that we removed because AMN was defined only for m and n not equal to 0, 0, or 0, 1. Those last two terms are easily handled, and you end up getting this. We now examine the other term. we now examine this other term, this one, which of course we can rewrite this as a limit as capital N goes to infinity of the same sum with n between minus n to capital N. And of course, n is not equal to 0 or 1. The point is that this is a telescoping series. That's the punchline. And so these things will cancel. So this term will cancel out with this when you keep on adding, but you're taking the summation from minus n, minus capital N to plus capital N. And therefore, so the sum telescopes, most of the terms cancel except the endpoints. There's some endpoints that you have to worry about, and you pick up those endpoints. Okay, so the last two endpoints, telescopes, and we finally get one over z limit what we end up getting. And so we see from here that the first one is pretty clear. It's going to be just 2 pi over z cotangent pi over z. And the last term is going to be minus 2. And then you have to work, and these two terms, of course, go to 0. And so you have to now calculate plus 1 over z limit n goes to infinity. Well, it's minus because of pi cotangent pi n plus 1 over z minus pi cotangent pi n over z. And for this you just write down, so cotangent pi, and let's just do pi n over z for the time being. Let's just do this calculation first, okay? What is that? Well, it's cos over sine. That's e to the I pi n over z plus e to the minus I pi n over z over and I guess there's an I somewhere, so there's probably an I there somewhere. Okay, get that. And this you can rewrite by multiplying top and bottom by e to the pi n over z, so you get e to the 2 pi I n over z plus 1 over e to the 2 pi I n over z minus 1, which I can rewrite as I times, well, this is take the common thing, which is minus 1 plus 2 over e to the pi I n over z minus 1. Everybody okay with me? This calculation is pretty routine. And now the point is this, that z is in the upper half plane. Okay, so z is in the upper half plane, so you can rewrite this as, so if I write I as minus 1 over I, you can see that since z is in the upper half plane, e to the pi I n over z is equal to either minus pi n over iz. Yeah, that's correct. Right? And z goes to minus 1 over z is in the upper half plane. So a little reflection shows that this guy, in over z, so this part here is equal to I n over z. By a simple calculation is I n x minus iy over mod z squared. So the point of the matter is I times I is minus 1, I times minus I is plus 1, y is positive, and that when the n, it's a positive coefficient for capital N. So as n goes to infinity, this goes to 0. Okay? So you pick up an I from that. All right. And when you pick up an I from that calculus, so each one contributes an I. So finally, we end up getting 2 pi I over z. So finally, because there's a pi in front here, okay, and a pi in front there, we're going to pick up a pi times I. So we get so this is a theorem. So G2 of minus 1 over z is not equal to z squared times G2 of z. It's that plus this fudge factor. So this is an example of what's called a quasi-modular form. It's also an example of a mock modular form, but we won't get into that, but which is again something that Ramanujan hinted at. So that means now we know exactly how G2 is transforming. So even though G2 is not a modular form of weight 2, it is pretty close to it being such a thing. And so we normalize, we define E2 of z to be 1 plus 1 over and so I'm going to leave to Karamdev to calculate now, like we did before, the Fourier expansion of this series. So as before, using Lipshitz's formula, we derive the Fourier expansion of E2 and it turns out to be equal to 1 minus 24 summation n going from 1 to infinity sigma of n. So sigma 1n is some of the divisors of n. That's the so you remember Lipshitz's formula? You know, it gives you an expansion of this, and you can use the Q expansion to get finally that it looks something like this. So this is the kind of missing link that we didn't have. All the other ones were nice Eisenstein series, but this is not this is an Eisenstein series, but it's not a modular form. All right. And so if you want to rewrite our theorem in terms of E2, you have a corollary that E2 minus 1 over z is equal to z squared E2 of z plus 6z over pi I. By the way, this proof that I'm giving you of Ramanujan's first two conjectures are not the Mordell proof. This is now essentially 20th century simplification of all this stuff, and pasting together lots of people's observations. Okay, so we now have the famous theorem of Jacobi, which of course Ramanujan was aware of. And that is this delta that he defined has this expansion. So we now are in a position where the Eisenstein series E4 and E6, which were defined earlier, we know they were modular forms of weight 4 respectively, weight 6 respectively. So this is a weight 12 thing, and it's a Cuss form, and it starts with 1. That's the 1728. So this much part of the theory we're familiar with. But the fact that this guy can be written as a product is something we haven't seen yet. And the question is, how does one do this? And this is the way I'm going to do it. This is not the way Jacobi did it or other people did it. So we'll prove this. Let f of z be the product that you have so here again, as always, q is equal to e to the 2 pi I z. Okay, because q is equal to e to the 2 pi I z, and this is a periodic function with period 1, f of z plus 1 is equal to f of z, right? So clearly, f of z plus 1 equals f of z. Good. If we can show that f of minus 1 over z is equal to z to the 12 f of z, then we know then that for a modular form, because 1, 1, 0, 1 and 0 minus 1, 1, 0 generate, this will imply that f is a modular form. In fact, f is a Cuss form because the expansion starts at q. Okay, it vanishes. So f is a Cuss form then of weight 12, because that's where this 12 is coming from, on the full modular group. And because we know the dimension formula, which we derived last time, that the space of Cuss forms is one-dimensional, it has to be a non-zero multiple of this guy. And then comparing Fourier coefficients, you end up getting this. Okay? So the only tricky part then is to show this. So to that end, what we will do is we take this thing and logarithmically differentiate. Okay? So take logs and differentiate. See, the process of logarithmic differentiation, you don't have to worry about whether you can take logs or not, because logarithmic differentiation just basically means f prime over f, for which you don't need to discuss whether the log is defined or not. So f prime over f although in this case we can see that product doesn't vanish because we're sitting in the upper half plane, but that's a minor point. Okay, so when you do this calculation, you will see that f prime over f, so the first term is take logs, that's log q, take the derivative, it's 1 over q, but we're taking the derivative with respect to z. So it's 1 over q times 2 pi I z, yeah. So you get 2 pi I minus 48 pi I Now I expand this guy in terms of a power series. So q to the n, 1 minus q to the n, can be expanded as a power series. Now let's put the q to the n outside. So this is just q to the, and j is going from 0 to infinity. So that's equal to q to the n j plus 1. Now j is going from 1 to infinity. Okay, and now I group together. There's an n here. Sorry. Okay, go back. Put this n back in. Oh well. No, this is fine. Let's simplify this as follows. So now I'll still need that. That's why I'm not erasing it. So this then becomes equal to 2 pi I minus 48 pi I times summation n going from 1 to infinity, j going from 1 to infinity, times n q to the n j plus 1. Just put the things together. Now I group together all the numbers of the form n times j plus 1, right? And both of them are bigger than or equal to 1. And I group them together. This thing can be combined to one sum going from 1 to infinity, q to the m, and inside I am looking at the factorizations of m as n times j plus 1, and those are the divisors. So d divides m, you get this, and that's exactly this is looking very close to this. So what we get finally is that this is equal to 2 pi I. Yeah, 2 pi I times 1 minus 24 summation n going. Well, let's change variables now. N going from 1 to infinity, sigma of n to q to the n. So therefore, this guy is f prime of z over f of z is equal to 2 pi I times E2. Okay, so we get the corollary. F prime of z over f of z is equal to 2 pi I times E2 of z. Okay. And now, because I'm interested in calculating f of minus 1 over z, it makes sense to try to put minus 1 over z into this fact, and then try to use the functional equation that I already know for the Eisenstein series to get it for this one. Okay? So from here, we see that f prime of minus 1 over z is equal to 2 pi I e2 of minus 1 over z. Just change z to minus 1 over z in the equation. You get that. But I know what this is. This is equal to 2 pi I z squared e2 of z plus this fudge factor, which was 6 pi I, whatever it was, 6z over pi I. From the previous calculation. Okay, so you get this. because that's the transformation law for E2. All right. And so this comes out to be, well, this is equal to z squared 2 pi I times E2. 2 pi I times E2 is here. The pi I here cancels, and I get 12 times z. 12 times z. Everybody okay with this? And interestingly enough, if I divide out by 1 over z, and think of 1 over z squared as d of minus 1 over z. Okay? And of course, f prime of z, you have that. So we divide through this, d of minus 1 over z, plus z. So dividing out by that. So when you integrate, we find that integrating, we get that integrating, we get f of minus 1 over z. See here you get log of f of minus 1 over z equals log of f of z plus 12 log z. So you and exponentiate the whole thing, you get z squared, z to the 12 times f of z. There's a up to a constant lambda, but then you compare the behavior at infinity and you find that the lambda is equal to 1. Okay? So this is what you were after, and we got it using the functional equation for the Eisenstein series of weight 2. All right? Any questions on this? Yes?
I think that J starts from, when you write J equals to 1 to infinity, it's n J instead of J plus 1.
Oh, yeah, thank you, yeah. Here's j equals 0 to infinity. Thank you, yeah, that's right. Yeah, it was j equals 0 to infinity. Thank you.
Then here, in this line, they are all equal.
Oh, yeah, sorry, yeah, thanks. Yeah, thank you. All right, so that's the proof. This is not Mordel's a way of, or Jacobi's way of doing this. Now I'd like to look at several consequences of this remarkable equation. So starting from that product, that infinite product with the Q expansion, you end up getting the Ramanujan formula. So rather neat. Here's an important exercise which is worth doing. Let eta of z be show that where the square root is chosen so that it is the branch with non-negative real part. So this is called the Dedekind eta function. So Dedekind was already familiar with this function. In fact, he knew that the transformation rule, if I change z to az plus b over cz plus d, that transformation rule is complicated. Dedekind knew that. In fact, some of you may know about Dedekind sums. The root of unity that appears here, after the transformation, gets messed up quite a bit, and the behavior of that root of unity is given by what are called Dedekind sums. I think Ramanujan was aware of that, but there are always 24 roots of unity, so that explains why you take the 24th power to get rid of those Dedekind sums. I think that was part motivation for Ramanujan's study of the 24th power. Turns out then it's important for other reasons too. We will discuss, we'll try to prove the first two conjectures of Ramanujan. So to do that, we'll discuss Hecke operators of level 1. Well, as I told you, if Mordell had asked himself what's the big picture or what's the general principle that was behind this work, we would be calling them Mordell operators today. All right. So let X sub m be the collection of 2 by 2 integer matrices of determinant m. Okay, so if I have a 2 by 2 integer matrix of determinant m and I hit it with an SL2Z element, I'm still back in the same space because the SL2Z element has determinant 1 and it has integer entries. So SL2Z acts on Xm. We'll keep it as a left action. Okay, left will be on the left, say. Doesn't matter, you can act on both on the right or the left. And we want to show, we'll show that the number of orbits is finite. For this action, orbits is finite. And the representatives are given by. So you know that once you have a group acting on a set, you can decompose the space, the set, as a disjoint union of orbits. So we'd like to look at the representatives. So X sub m turns out to be equal to a disjoint union of these factorizations of m Since I've got left action, this is why I'm writing it like this. So you have, these are your representatives, A, B, 0, D. And how many are there? Well, there are D representatives for each one. For each, once I fix the factorization, I've got D of them, and I sum over D dividing M. So the number of orbits, thus the number of orbits is summation D divides M, which is equal to, in our notation, sigma 1. So essentially this is evident in the Mordell's paper, but Mordell didn't step back and say what's going on. So this was first observed by Hecke. And I'm going to leave Karamdev, you're going to do this, okay, in the tutorial. It's no big deal, okay? So just, yeah. So this is really an exercise to figure out these are your representatives for the action. So, okay? So I'm going to leave this as an exercise. Now, once we have this, we can define some remarkable operators. This is the key. So we already observed that you have your MK of the full modular group. These are vector spaces. These are vector spaces. We found that out last time. They're finite dimensional vector spaces, right? And now we're going to introduce linear operators using these representatives. So are defined as T sub m of f. So f is a modular form of weight k. T sub m of f is defined as m to the k over 2 minus 1 summation AD equals m. D, of course, positive. So here also D was positive divisors. And B mod D F slash AB0D. So I have to show you that if you take a modular form of weight k and you do this funny thing on the right-hand side, you still get a modular form of weight k. I have to show you that. And this is where the slash notation comes in handy. So we need to show that the right-hand side, abbreviated as RHS, right-hand side is a modular form of weight k. In other words, i.e., need to show Tm of f slash gamma is Tm of f. Remember, using the slash notation, the modularity condition is neatly expressed as f slash gamma is f. That's what we need to show. Okay, so we need to show Tm of f slash gamma is Tm of f. So that means that I take the expression on the right-hand side and I slash it with gamma. And now you did that exercise. If I have f slash gamma 1, gamma 2, remember, in SL2R, that was equal to f slash gamma 1 slash gamma 2. You had this kind of property, property of action, actually. So you have this. So if I slash this thing with gamma, then I'm really looking at AB0D slash times gamma, right? So the question then is, what happens as I run through all these representatives, AD equals MB mod D, and I have a fixed gamma, how are these representatives changing? And it's no big deal to see that they're going to be changing again to other representatives. You'll have, okay? So now the question is, so I should be able to, so let me just spell it out neatly here. Clearly, SL2Z acting on X sub m, operating on X sub m, is the same as this. In other words, I can write, if I have an element AB0D and I have an element in SL2Z, let's call it RSTU, then this is again an element in X sub m, and therefore must belong to one of the orbit spaces, right? That's what the decomposition is, right? So therefore I should be able to rewrite this silly thing as A prime, B prime, 0, D prime times some other matrix in, let's call it R prime, S prime, T prime, U prime, okay? Where this is now an SL2Z. Okay, now you can see what I'm going to do. If I need to slash this by gamma, so thus f slash AB0D slash gamma, here's my gamma, it's equal to f slash gamma prime, call it, which is this one here, times another matrix, another representative in this orbit space, right? I mean, these are the representatives. So now, but gamma prime is an SL2Z, and I've got a modular form for the full modular group, so f slash gamma prime is equal to f. And now the only question that remains is that if I do this little trick, fix a gamma, and I hit all these orbit representatives by this fixed gamma, the new orbit representatives that I get are going to be one-to-one correspondence with the old ones. I mean, that's just a small exercise which I think you can actually leave it to them to do. It's not a big deal to do. All right, so you end up getting that, and therefore Tm of f is actually slash, it goes into the space of modular form. So this is a remarkable device, and it was implicit in Mordell's paper. It was implicit in Mordell's paper, but not written down explicitly. All right. So that's why I keep telling my students, perhaps when you finish proving a theorem, you should sit back and say, what is it that I've done? Instead of just saying, let's now go play ball or something. You should ask yourself, what is it that you've done? And maybe it might require you to stand back and look at it again maybe after a couple of months, instead of saying, oh, I've done that, it's over, and nothing more to do. The other point that I want to make is that, in fact, this is a linear transformation from the space of cusp forms to cusp forms. In fact, T sub m also maps Sk as SL2Z. In other words, well, we already checked it's a modular form. What does it mean for it to be a cusp form? It means that you have to show it vanishes at infinity. So, i.e., we have to show that if f vanishes at infinity, so does Tm of f. So in order to do that, we have to calculate the behavior of Tm of f at infinity, the Fourier expansion. So to do this, we need to compute the Fourier expansion of Tm of f. And this is not terribly difficult. So let's just do that, and let's just do the obvious. So a little elementary exercise before I start this. If I take the dth roots of unity, this looks very elementary. It's just the sum of the dth roots of unity. And you can see that if n is divisible by d, these are all just ones, and you pick up a d. If they're not, you get a permutation of some primitive dth roots of unity, and then you partition it and you get that's 0. But I'll leave that to you to check. So now, suppose f of z is equal to summation n going from 0 to infinity lambda of n e to the 2 pi I n z. So that's the Fourier expansion. Suppose that is the Fourier expansion of f at infinity. Then we just need to calculate what's going to happen. We just do that. I'll just indicate the highlights. So here we have Tm of f of z then is equal to m to the k over 2 minus 1. AD equals m, d positive, b mod d, b going from 0 to d minus 1, lambda of n, e to the 2 pi I, n, I have to replace z by az plus b over d. Az plus b over d. And of course, you know, there are all these fudge factors that go with this thing. The fudge factor that goes with the slash operator is that the determinant to the k over 2, right? The determinant to the k over 2. That in that case, AD is equal to m to the power k over 2, right? And times Cz plus d to the k, right? So Cz plus d to the k, that's just, wait a minute, Cz plus d to the minus k, right? The slash notation the determinant to the power k over 2, Cz plus d to the minus k, f of az plus b over Cz plus d. Right? That's the notation. That's just the notation. Okay, so keep that in mind. Make sure so therefore, the determinant is to the k over 2, but the fudge factor Cz plus d is, in our case, it's what is it? B0 d. It's d to the power minus k. Is that okay? Okay, yeah, good. Then f of well, and I just did that, so it's all there. Okay, so you end up getting these fudge factors, and if you observe something, let's see. Oh yeah, thank you. There's a sum missing. Thank you. The sum is over n going from 1, 0 to infinity. Thank you. So there's a sum missing. N equals 0 to infinity is missing there. Okay. So now what do? We obviously interchange summation and bring the summation b in here, and you can see it's going to be either 2 pi I n b over d. And I use this fact, and I see that it's going to disappear unless d divides n. So unless d divides n, it'll disappear. So this simplifies to, and not only that, when a d divides m, you're going to pick up a d. So that means when you clean it all up, which I will do fast because I'm running out of time, you end up getting AD equals m d positive, m over d to the k minus 1, summation n going from 0 to infinity, d divides n, lambda of n, either 2 pi I an z over d. So finally, collecting terms, you see, so d divides n, so write n, see d divides n here, write n as d times r, so that n over d is just r, and it's a summation over r going from 0 to infinity. And when you collect it all together, you find that this is equal to Tm of f is equal to what? S going from 0 to infinity. AD equals m, AR equals S, m over d to the power k minus 1 lambda of dr. So finally, this can be rewritten as, summation, oh, sorry, I forgot, e to the 2 pi I as said. Can be rewritten as s going from 0 to infinity of a divides m and a divides s, a to the power k minus 1, lambda of ms, see dr, ad times ar equals m times s, so dr is equal to ms over a squared. So this is it. This is the Fourier expansion of Tm of f. Okay, so we now know, if I knew the Fourier coefficients of f, I know the Fourier coefficients of Tm of f. And now if f vanished at infinity, which means that the constant term is 0, the constant term for this guy is also 0. Okay, so this shows Tm actually maps cusp forms of level 1. I'll keep using, okay, SL2Z, that's the way I've been doing it, into cusp forms of weight. That. Okay. Everybody follow this? Question? Okay. So, now I think we're ready, more or less, to deduce conjectures 1 and 2 of Ramanujan. So this is what was missing from Ramanujan's understanding, that not only is the space of modular forms of weight k a nice vector space, but there are these linear transformations on these vector spaces, and these linear transformations have this nice Fourier expansion, and therefore the question is, what do these linear transformations do on these so-called vector spaces? So we know that the space of cusp forms for the full modular group we already know is one-dimensional, and so it's spanned by the Ramanujan cusp form. We already know that. So now let's act by the mth Hecke operator. So if I calculate the mth Hecke operator on delta, it has to come out to be some multiple of delta, because it's a one-dimensional space. Okay, so let's try to calculate what that coefficient is. So this is telling me that, for example, let's calculate the nth coefficient of both sides. Calculate the nth coefficient of both sides. Well, we know what the nth coefficient of this guy is. We know what it is. It's tau n. And we know what the nth coefficient of this guy is from this formula here. The nth coefficient, well, it's the sth coefficient here, but anyway, you'll see. It's d divides m and d divides n of d to the power 12 minus 1, which is 11, times tau of m times n divided by d squared. Right? I have to calculate that. Everybody follow this? It's a beautiful calculation. Now, put in n equals 1. What's the first coefficient of the Ramanujan cusp form? 1, good. So tau 1 equals 1. So put n, this is true for every n. Put n equals 1. And you get tau of 1, which is 1, times lambda m equals, let's see what happens on the left-hand side. We're putting n equals 1. D has to divide m, and d has to divide 1. There's only one choice, 1. So d equals 1, but this side is tau m times 1 divided by 1, so this is tau m. So this eigenvalue of this mth Hecke operator is actually tau m. And therefore, I end up getting the relation tau of m times tau of n is equal to summation d divides m and n, d to the power 11, tau of mn over d squared. So this is the formula that I get for all m and n. And when m and n are relatively prime, if m and n are relatively prime, what does this right-hand side do? Well, d divides 1. That's the only choice. And that means d equals 1, so you end up getting tau mn is tau of m times tau of n, which is the first conjecture. So you get this. So now this is proved, and I will, because I'm running out of time, I will let you figure out for prime powers what to do, because for prime powers it's pretty easy. You can just now calculate by some sort of recursion procedure. If I have p to the alpha and p to the beta, you can figure this out. The common divisors are going to be the minimum of the two powers, and you can get a recursion floating around. So I would recommend to do the exercise to get conjecture 2, to get 2 of Ramanujan. Put m equals p to the alpha alpha in that, and put n equals p, and deduce the formula. Then you'll see that the GCD of p to the alpha and p is just p, and there are only two divisors, and there will only be two terms on the right-hand side. So that takes care of that. Now, I am running out of time. I did promise you, can I have 5 minutes and maybe 5 minutes? Oh, yeah, okay, yeah. Okay, so I did promise you that estimate for number 3, which was power p to the power 6, right? So I'll do that. It won't take long. It will take only a few minutes to make that observation. So we have this basic observation. If f is a cusp form, then y to the k mod f of z squared is SL2Z invariant. So I'll leave this to you. It's essentially calculating something that Karan Dev did the other day with respect to the measures and seeing how things change when you hit it with a group transformation. So you do the same thing. You hit it with the group transformation, see how y changes, see how z changes, and then use the modularity, and then you end up getting that it's SL2Z invariant. Okay. So now I've got a modular form of weight k, and let's say it's a cusp form. So f of z starts off by n going from 1 to infinity. Let's say a n e to the 2 pi I n z. And I'm interested, so I look at f of x plus iy and think of it as functions of real variables x and y. That'll just simply be n going from 1 to infinity, a n e to the 2 pi I n x, e to the minus 2 pi n y. Is it okay?
It's supposed to be a class here, but nobody's here.
Oh, okay. Okay, well, it'll only take a few more minutes. I should be done in a second. So here, what you should do is you should look at this as a Fourier expansion with y fixed as a function of x, okay? And so I can calculate the nth Fourier coefficient. The nth Fourier coefficient is either a n e to the minus 2 pi n y, and it's equal to the integral 0 to 1 f of x plus iy times e to the minus 2 pi I n x dx, right? This is the Fourier coefficient. Everybody okay with that? Calculate the Fourier coefficient. I end up getting this. That's what you get. Now, I want to estimate it. And the integral, so I'm going to use this fact, so that y to the k mod f of z squared is SL2Z invariant. So I look at what it's doing on the fundamental domain. The fundamental domain, apart from that point at infinity, when you combine it, it's a compact domain, and therefore the function has a maximum on that space. So let m be the maximum. So therefore, this guy is bounded by some fixed m for all z in the standard fundamental domain. So in that case, I'm just basically saying that if I have this will tell me that f of x plus iy is bounded by m over y to the k over 2 for all such elements. And so this is going to be bounded by some constant over y to the k over 2. And now this is valid for any y. I pick y to be 1 over n. Okay, so 1 over n, that essentially is e to the minus 2 pi, and I end up getting that this implies that an is big O of n to the k over 2. Big O means some constant times n to the k over 2. So in general, for a modular form of weight k, you end up getting this estimate of n to the k over 2. Okay, so that oh, they are here. Okay, I better stop. Okay, thank you.